Hi everyone, and welcome. So as you probably know, in NVMe-oF environments, improving high-speed data transfer into multi-core systems is a well-known challenge. Methods like network adapter offloads and performance tuning are effective practices in this domain, and a lot of attention has been focused on how to set these parameters and which offloads to select for higher performance. So today, we will focus on how to gain NVMe-oF system performance through smart CPU Core Affinity settings, generally by using smart mapping between software and hardware threads. Better resource utilization can be achieved. So my name is Adi Folkman, and I'm a technical product manager in the Kumuscale shared and accelerated storage software team at Kioxia. Kumuscale implements fast networked NVMe-oF flash storage servers to achieve native NVMe-oF performance at data center scale. I have a BSc degree in electrical and computer engineering and a master's degree in law, technology, and business innovation. And actually came all the way from Israel to be here with you today. So our overall agenda for today is talking about a software-based mechanism that aims to optimize results and achieve performance scalability through CPU Core Affinity settings. We will start off with understanding what is the actual problem that we're trying to solve, and also discuss what exactly is CPU Core Affinity. I will also suggest a solution, proposal, and best practices. And then, last but not least, we'll address performance results with enhancements from real-life profiles and results. So, as we know, typical storage servers, and specifically storage servers, generally have a CPU with a certain amount of cores and dedicated caches, memory, storage, NICs, and more. And when a storage server receives requests from the NIC, it accesses the SSDs, gets the data, and then returns it back. In order to handle high storage and network traffic, we need more software threads. The more threads we have, the more contention we have on the hardware resources, such as the cores and the caches. As much as we want a bigger CPU and add more cores, we will end up with scaling issues because they will have to share the same resources like the DDR and the PCI buses, which will become a bottleneck. So we can understand that there is a limitation here. And this is the reason a non-unified memory access, a NUMA architecture, is suggested. A NUMA node consists of a CPU, private memory, and peripherals such as the PCI, and this allows it to access its own memory in a fast and efficient way. NUMA nodes can access memory and peripheral devices attached to other NUMA nodes by a node-to-node interconnect, but this will affect timing and make the process slower. This NUMA architecture allows us to build larger systems and which are asymmetric and therefore will require a more complex scheduling approach. As we can see here in the diagram, which I've attached in the slides, we have a system with two NUMA nodes. Each one has a CPU with a few cores, and each core has its caches, and it is directly attached to the memory and connected to the storage and NIC through the PCI. So this right here is called a NUMA node, but now if a thread is scheduled to a core in a different NUMA node, due to context switching, we won't just lose the caches as before, but also suddenly threads will be far away from the memory that they need. So think of a situation where a thread runs on a core, for example, on the left-hand side, and needs to use the memory also on the left-hand side, and a certain SSD, which is also located on the left-hand side. it will be inconvenient and also inefficient to move it to a core that is located on a different size, because each time it will need to communicate with it, it will have to go through the QPI. So if previously our problem was that we only lost the cache, now we are also drifting away from the memory, which will add latency and another bottleneck in the QPI bus, and both of these affect performance. In other words, as we have much more threads than cores, the context switching becomes a root cause of performance loss. So we actually have motivation to make sure that a certain thread will always run on the same core or on a group of cores. Otherwise, we will kind of pay the price of moving to a different NUMA node and accessing the memory and the storage over there. So overall, all of these cause limitations that will lead to underutilization of the system resources, mainly the SSDs and other resources as well, which means that you're not fully utilizing all of the computation power and resources which are already available in your system. So after we've covered the challenges, let's talk about what is CPU core affinity. Affinity is a controllable per thread property, kind of a mask which defines where, in terms on which cores, threads can run on. The operating system scheduler will manage the scheduling only to the cores which are defined according to the thread's affinity. So leftovers from of a process that was running on a given processor may remain in the processor state, like the data in the cache, even while a different process is running on it. So if we were able or are able to schedule that process to run on the same processor, we can improve its performance by reducing performance degrading events such as cache misses. So we have here in the slide over here, let's assume we have three applications, application A, B, and C. And in the default scenario, which you can see down below, we have a few cores. Each one of the apps has many threads spread across the cores, and keep in mind that the cores might belong to different NUMA nodes. So as we are working in the NVMe-oF environment, we want, as we all know, to minimize the latency to the storage. So we would not want to waste time within the server in order to access a different NUMA node if this is a situation that we can avoid. So when we use a server that supports the NVMe-oF protocol, the software layer that manages the server resources implements the NVMe-oF protocol on the server side, as we know, and this is reflected as an example in any action involving the storage devices and mainly the SSDs. So let's assume we get a request to read data, we access the SSD and get a response in a certain time frame. If a context switching procedure would happen, a thread would appear in a different core and even on a different NUMA node, which suddenly would be farther away from the SSDs, which is something that leads to bigger variance in the latency and may affect latency-sensitive applications. Once we use CPU core affinity and pin certain processes to specific cores, we can ensure that dedicated cores are used for a specific application's threads. So this way, we can make sure that accessing the system's resources, like the storage or the memory, is done in a managed and unified manner, which will lead to overall better performance, which is something we're looking for. So in other words, with CPU affinity, we can actually bind a process to a particular CPU, which will increase the cache hits and the overall system performance. As the NVMe-oF layer is the main software layer that is sensitive to hardware and sensitive to hardware resources in terms of sharing and availability, this will affect performance under both TCP and RDMA transport types. So after we've talked about what is Core Affinity, let's talk about the key benefits while working in an NVMe-oF environment. As we know, overall, the fabrics layer allows us to use a scalable transport layer that is able to separate the storage from the compute nodes. And once we use CPU pinning, we can maximize cache efficiency and improve both the memory access speed, because we are already in the desired NUMA node, and also SSD access, because we are already in the right place and will not need to go to and pass through the QPI. We can also benefit from separations from noisy neighbors in a way that threads may be noisy as they access the memory, the SSD, and the caches. And a lot of times, and then when we come back to the core after these threads, it becomes disorganized. Once we use Core Affinity settings, we have a way to prevent this kind of behavior. Instead of not knowing which thread, when, and where will disturb another thread, we can make sure which NUMA node is used per thread and then manage it in a smart way. But as we can expect, there is a trade-off. It's not an easy task to know how to configure these settings in a way that will result in higher performance. Each platform needs its own tuning in order to reach optimal settings, and there are several aspects to take into consideration, like available hardware resources, such as the number of cores, the NUMA nodes, the NICs, the memory, and also sometimes the transport type, application types, and also the workloads. So actually, two systems with the same number of cores and the same number of NUMA nodes may behave differently due to, for example, different caches, internal buses, and more. Also, another thing to take into consideration is that reaching valuable Core Affinity settings for a certain platform is not something which is permanent or fixed in time. The reason is that these settings are dependent on available resources, workloads, clients, connectivity, and other aspects that might change over time. Also, I would recommend you to keep in mind that overworking busy CPUs might affect both the application and the system performance. Okay, so as far as an industry perspective, overall, there are many evidence that setting Core Affinity has a significant impact on processing efficiency. While different types of configurations will perform differently, our team at Kioxia were able to identify this variance in results. While working on the same platform in a given setup, there was a difference between not setting the Core Affinity settings at all, setting this Core Affinity settings with certain values, and then changing them. Each time we got different results, and we saw a dramatic variation. So the overall performance that we were able to gain by optimizing these settings was not something which is neglectable. Also, another interesting thing was that we found a difference between TCP and RDMA. In TCP, the more core we used, this led us to better performance, while in RDMA, we had to find a balance. Using a small amount of cores reflected in lower performance, while using too many cores also resulted in lower performance as well. So these changes made us reach a conclusion that we had to develop an automatic mechanism to allocate between minimum and maximum cores per link based on the system's spec. But anyways, in both cases, we've learned that we need to reserve at least one core for other services executing in user space, such as management, for example, for logging and handling REST requests and more. And otherwise, kernel threads which have priority over user space threads. So we saw that the system in some cases did not respond or may not respond if these threads are not scheduled on time. So this work was kind of dynamic and quite interesting. Also, there are some challenges that we as an industry have to deal with. The most common case are to identify and to follow new technologies and architectures and system topologies. For example, new processors have, for example, frequency scaling technologies that allow scaling up of specific cores on demand, and having this feature embedded in the CPU hardware means that the CPU affinity settings will probably make a dramatic difference in performance. Also, as an industry, we must look forward ahead to the future, which will probably include setting CPU affinity in systems with many cores, some of which are optimized for different processes. Instead of having a standard CPU with, for example, n identical cores, in an asymmetric system, different cores are optimized for different use cases and in order to optimize the power consumptions. And these systems are already available. It's a trend. We know that in some cases we want to use both high-performance cores but also low-power cores, sorry. And when we bring into the picture affinity settings, it makes the process of finding the right settings even more complicated. We're not only trying to apply smart core pinning, but also need to take into consideration which core is suitable for specific operations. So therefore, managing the CPU affinity in these cases becomes a very complicated task and not a trivial task to deal with. And based on this aspect and all the other things we've talked about earlier, we can conclude that there is a real-life need to automate this process. And also, we will also want to make it adaptive in a way that will enable it to be dynamic and adjustable per platform and use case. For example, if we use a static affinity settings, and for some reason in a certain time period only one NIC is active and transmitting, cores pinned to other NICs are in idle state, and this is a situation that we want to avoid if possible. So up till now we've talked about the problem, how Core Affinity solves it, and as we talked about earlier, our motivation was to optimize CPU utilization in order to gain performance on different platforms. We covered the benefits, but also the challenges of setting CPU core affinity, which will eventually lead to higher CPU utilization in multi-core systems and results in better performance characteristics such as IOPS and latency. If we focus on storage servers, we can understand that these settings will enable hardware resource reservations and guarantee quality of service by avoiding storage device underutilization. And we also talked about how we are able to leverage from non-unified memory access architecture in a way resources may be accessed locally and therefore allow application threads to be executed on the CPU core, which is closest to its memory, or to the NIC, depends on the application and the setup considerations. So our team at Kioxia were able to develop a solution that suits our software called Kumuscale, which implements a networked NVMe-oF flash storage service to achieve native NVMe-oF performance at data center scale. I cannot discuss the implementation or deep dive into the details, but I will try to give you a few high-level guidelines which may be useful for you as a baseline for you to start from. So as part of the development process, we've noticed that when we use all of the available cores and apply a large workload, applications that run in user space did not receive CPU resources because the kernel had priority over user space apps. This caused kind of a starvation. The system did not respond in these cases, and this behavior led us to a conclusion that we must reserve at least one core for other services, such as the management for logging, handling REST requests, and more. So I would suggest for you to define and design according to the desired total number of cores reserved for management in a way that the reserved cores are evenly distributed on all NUMAs or located on the NUMAs that are not attached to any interface used for data transfer. In our case, we have developed an automatic logic that takes into consideration system properties like the transport type, the number of NICs, the CPUs, and NUMA nodes, and makes the decision of core assignments to the NICs, We need to remember that this decision is dynamic and changes between platforms and also dependent on the system properties. The pinning itself takes place right after the initial connection, and the pin threads are kernel threads that handle the traffic from or to the network and the SSDs. And we are able to pin interrupts also to specific cores in a way that specific cores will handle the traffic of specific NICs. Also, try to look at it as an optimization problem, which may be solved using a cost model, for example, which will output an optimized set of parameters according to the setup. The outcome of this optimization problem will be an automatic and adaptive process, which will set the core affinity in a clever way based on machine learning technologies. But we need to take in consideration that even if we figure out this information, we'll still have a hard time to get or generate data for many systems and capture many scenarios and different loads, CPU, cores, caches, buses, and more. That's the general concept, but it's out of scope, so maybe next time. So just before we conclude the session, I just want to briefly show you an example of the performance enhancements that we were able to reach in Kioxia. We used the Dell 7525 platform with 2 AMD EPYC processors with 32 cores using the PCI 4.0 architecture, which actually means that we have 60 NUMAs, where 4 cores assigned per NUMA. And our testing setup includes a total of 4 over-the-network clients executing btest as an I/O generator. That's the diagram. And here we can see the results of the same tests, both in RDMA and in TCP. We can see a dramatic impact of the CPU core affinity settings. For example, if we focused on the results of 100% reads, we can see that in RDMA we reached about 5.2 IOs, while with smart CPU affinity settings we were able to see almost 8 million IOs. In TCP, we reached about 1.6 million IOs, while with CPU core affinity settings, we were able to see almost 3.8 million IOs, which is more than double, which is very significant. And note that the core affinity has a bigger impact in TCP. It makes sense because the TCP is implemented in software compared to the RDMA protocol, which is the hardware, which has hardware offloads, so it is expected to gain less from software optimization implementations, but still we can see that it is helpful in both transport types.